So I want to emphasize, first of all, the point that I want to talk more on engineering than science. Of course, we all try to do new science, but eventually we have to build something. So this is content what I want to cover. I'll try, but I'll start from what is the motivation, from where we are coming, what kind of process we need to have for establishing this nanophotonics. And I'll touch upon monolithic and heterogeneous integration, mostly with SOI, that is becoming sort of a material choice. As the previous speaker, I hope he convinced you silicon is not dead. And then at the end, I will touch upon formalism to evaluate the Purcell effect to avoid some confusions that we detected in the literature, and I conclude my presentation. So our work has been driven by two major applications. One is optical interconnects for chip scale multi-core computing, and we have been working towards this goal for quite a few years. We collaborate with industry, and if you go in Sandia National Lab and look up at what is the power that you need to feed a supercomputer, you end up with a power station. So certainly we could save some energy, and the issue is mostly dissipating the heat than anything else. Never mind, people will tell you, oh, we are saving energy. No, they cannot dissipate the heat. So that's where the optical communication may come handy, reduce the amount of heat generated. And this brings me to the second application that actually is the data centers, which is part of our work in NSF Engineering Research Center for Integrated Access Network, where about 6-7 years ago, we for the first time introduced optical switching in data centers. We started with this Helios system that we built using MEMS, and this was basically overlay of a circuit switch with a packet switch. So short flows went through the packet switch, and long flows went through the circuit switch, which was all optical using MEMS, just a mirror that pops up. And unfortunately, the flows had to be too long to justify why a millisecond response time is good. So we went on and tried to get to a microsecond response using WDM technology, and we actually demonstrated the second system. We called it MORDIA. M stands for microsecond. And then the flows are more or less the flows that the data center on average wants to switch at microsecond rate. So that's a good thing. Now, I'll try to look where we are going from here and from here in the future. And I borrowed this information from a semiconductor industry strategy symposium early in 2013, where they are projecting that basically in 2020 they will need to integrate nanowires, 3-5 semiconductor devices, and as well as put a photonic network on top of logic and memory devices. So that's an interesting observation. And we also were trying to see where we are going in the data centers technology, and we found that the top-of-the-rack switch would be great to integrate electronics and photonics very closely on the same material platform. That would be a real application, provided we can reduce the cost, which is today prohibitive to use these technologies. So given these two motivations, I want briefly to mention the nanophotonics process that we have been developing for the past, I barely remember, probably 20+ years. And the idea is to use lithography, high-resolution lithography, to write optical functionalities in materials, as well as defining novel devices. And the key is utilize near-field optical interactions that open up some unique new features to construct devices that otherwise would not be possible or will not be functional. So, however, there are a couple of challenges, as usual. We want to localize optical fields, optical modes, and Professor Fauché mentioned this slot waveguide as one localization technique. There are many more. And localizing the optical modes and overlapping with the material you want to interact, that's a good thing, and I'll try to reflect to it later. And there are, of course, opportunities, as I mentioned, monolithic, heterogeneous, and nanoplasmonics I'm not going to touch today. So this is basically a generic view on what we need to do. We need to construct a network on a chip. We need to have lasers, sources of radiation, ideally at different wavelengths. We need to construct modulators, passive optics for filtering, multiplexing, demultiplexing, all different types of light manipulation. And then at the receive end, we need to be able to demultiplex and also detect these signals. So, so far, the modulators made in silicon are utilizing the PN junctions and reverse bias, and they are getting to gigahertz, 10 gigabits per second rates, which is great. But if we want to go beyond 10 gigabits per second, that will be difficult. Also, the heat generation may become an issue. The second element is very small lasers that can be integrated with this silicon photonics platform. Basically, the approach we are taking, and I will reflect to it in the next few slides, integrating 3-5 semiconductors with silicon and making lasers out of it. So coming to the monolithic integration, I will very briefly overview what do we have in mind. We basically start with SOI platform, the thin layer of about 200, 250 nanometer silicon on buried oxide layer of 2-3 micron on silicon wafer. Then we do lithography, and what we did years back is define the structure on the side walls as opposed to two-step process on the top to make a resonant wire. And then you clad it with silicon dioxide, and you are done. You make a 1D photonic crystal. So we made these photonic crystals, and we introduced the quarter wave offset to make a defect. And then you clearly see this is measured 19 nanometers stop band with a transmission line in the middle, and the Q is not that high, but it's above 3,000. By the way, for telecom applications, if you want high bit rate, you don't want high Q. The photon lifetime has to be shorter than the modulation rate. So that's something to keep in mind. So I know in the abstract we were talking about discussing monolithically integrated pulse compressor, but I decided last minute to switch. I want to present some of the most recent results and very interesting ideas that we came across. This is basically what we want is to make a silicon electro-optic modulator that has a true Chi2 due to bonded electron nonlinearities. Then response time is determined by the electron's response time, which is in femtosecond range. So we can go over the terahertz eventually. Now, why is this? First time it was demonstrated in 2007. Here is a list of references that actually developed this technology. And the current results are very promising. However, there is a lot of work that needs to be done to be more rigorous in understanding the nonlinear characteristics of, say, strained silicon. And the application, as I mentioned, either electro-optic modulators or just three-wave mixing in Chi2 materials. So we did some work. I will very briefly mention the Pockels effect. Everybody knows it's a second-order nonlinearity. It can multiply two fields and introduce a nonlinear term in depolarizability in Maxwell equations. And these two fields can be both optical or one optical. One we call it DC, but the DC can be as fast as terahertz, DC compared to the optical carrier. So that's basically the Pockels effect. And where it's good, it has been demonstrated for this Mach-Zehnder arrangement. We could also do it in a resonant modulator, as I mentioned, as long as the Q of the resonator is not too high. And we actually did long time back work on three-wave mixing to convert time domain to space domain for ultrafast detection, and that could be a very interesting approach with silicon. So lithium niobate is material of choice so far, has a Chi2 of 360 picometer per volt, and it's one of the best materials. But if you want to put it on silicon, it's not trivial. So would be great to make silicon have coefficients of at least lithium niobate and have it on CMOS compatible platform. So what we did, we tried to analyze what happens, and it's actually, I'll give a very brief review. Silicon is a diamond lattice and is centrosymmetric and has no Chi2 coefficient. So to introduce Chi2 coefficient, you need to introduce a gradient of strain. So you perturb the lattice. So the lattice then will possess break the central symmetry and possess the Chi2 coefficient. And we calculated rigorously the tensor components, and these are the coefficients that we expect to be non-zero. Very briefly, how we make it. So we basically start with what I just mentioned, SOI platform. We spin coat HSQ, do E-beam lithography, remove the HSQ, get silicon, then we sputter silicon nitride layer using conditions that enable us to get a tensile or compressive strain of silicon. The main strain is appearing on the side walls of silicon here. And then we cover it with silicon dioxide. For testing, we use, again, one of these Bragg resonant structures. Basically, you have a Bragg mirror and a cavity. And we observe the stop band and the transmission lines introduced by the defects into the stop band. And as we apply electric field, hopefully the spectra in transmission will shift, and from the shift we can deduct the amount of delta N that we are getting. These are SEM pictures to show you that it's for real. And this is more or less the setup that I mentioned. We apply electric field, we use a tunable laser source, and we observe the shift of the resonance. So there are two transmitted curves, one for TE and one for TM, and this enables us to detect independently two different coefficients in the Chi2 tensor. And these are the results that we got from the measurements, and the resulting coefficients are 74 and 188 picometer per volt for, this is for TM polarization. All vertical components scales more strongly with the strain than the XXY component, which is the TE polarization state. So we did some more rigorous analysis of the relation between this strain gradient and the Chi2 coefficients, found the proportionality coefficients and so on. And it's interesting to notice that if you do modeling, you can see that in some regions around here, where it's red, you achieve a Chi2 of 1,000 picometer per volt. So brings it back. If we can localize the mode where the strain is, we actually beat lithium niobate by factor of few. So For the future, we looked more recently on some optimization. We defined figure of merit, the strain overlap with the mode of the field in the waveguide. And with simple scaling the size of the waveguide, you can see that figure of merit can be increased, but it's far away from being optimal. And I believe we have some new approaches that we are going to explore, and hopefully I will present it soon in one of the conferences. So now I'd like to shift to the heterogeneous integration with SOI, and I'll start from a large laser, a DFB laser on silicon. So the idea is the following. We basically take gain media, we bond it to silicon, and then we define the structure. And of course, beforehand, we remove the substrate, the carrier of the gain media. Then we define the structure, and when we calculate the modes, you can clearly see that it's about 50-50. So the mode gain overlap is about 50%. To know the evanescent coupling with other approaches is about less than around 4%. So that's a significant increase in the gain mode overlap, which is very critical for efficient sources. And for design, I'll just refresh your memory. So the lasing will occur in this gain profile. And with a DFB laser, we basically create a Bragg grating. And the lasing will not occur within the stop band. It will occur in one of the side lobes outside the stop band. So what we do in the design, we design the stop band to be close to the maximum of the gain of the media. So that's what we do. This is basically showing that under certain pumping condition, you can hit reflectivity larger than 1 in the DFB, which basically is showing that you have gain. The dependence is as a function of the modulation of the side walls. So 50-30 seems like optimal. The fabrication steps, we start from wafer bonding. We basically adopt the technique developed by the Santa Barbara group led by John Bowers. I'm not going to go through the details. I'll only make one comment that the toughest part is to clean the surfaces. The rest is semi-trivial. Then we do e-beam lithography. Then we apply 2 chemistries in RIE to go through the 3,5 and silicon and cover it with using atomic layer deposition with aluminum oxide to remove heat from the laser. This is an SEM of the fabricated device before the cladding. So this is silicon, this is INGA SPIE, and these are the experimental measurements that was optically pumped. So this is evolution of spectra as a function of pump level. And you clearly can see that the PL gets into amplified spontaneous emission and lasing. And to make sure it's lasing, we looked at log-log scale of light-light curve, and you see typical S-shape PL, amplified spontaneous emission, and lasing action. I'd like now to talk about making smaller lasers. This was 100 micron long, and to be sort of compatible with microelectronics, we want to make at least size of the wavelengths of light it emits. So that was the main idea. And we went in the literature and looked what are the candidates. There are lots of candidates. Disk is the best candidate. The only trouble is you make the disk small, your radiative loss goes up, and your Q is dropping down. So it's not useful when you want to really make it small, on the order of radius of 1/4 of a micron, 1/2 a micron. The next candidate is photonic crystal, which is great, but unfortunately, if I start removing the holes, the Q goes down. So the actual device size is determined by the hole membrane with the holes. There were a few other alternative approaches that are also very exciting, interesting work, but they're still on the micron scale. So on the sub-wavelength scale, there was pioneering work by Martin Hill back in 2007, where he took a pillar of gain media and covered it with metal to confine the mode. Unfortunately, it operated at a low temperature, and there was no clear path how to make it operating at room temperature. Same applies to the patch resonator by Ming Wu's group, and most recently work by Ning's group from Arizona State. He demonstrated a small laser with confinement in all 3 dimensions, but this is a Fabry-Perot-like mode, very sensitive to fabrication tolerance. Moment the sides of the laser are slightly off being parallel, the Q goes rapidly down. So our approach is slightly different. We looked at a composite 3D resonator with the goal to create a small laser at room temperature, sub-wavelengths in 3D, and isolate it from the surrounding. The main point is we wanted to use something realistic that can be achieved, which is order of 200 gain, on the order of 200 per centimeter. So this work was published about 4 years ago. More recent results on this work can be also found in the book, where it's one of the chapters on compact semiconductor lasers that was edited by Richard Delarue and company at Willy. So what's the basic idea? I want to go through a few details to share with you how we came to this idea. So using metal is a great thing. You don't use metal. You have evanescent tail in the air, so it causes less mode gain overlap. But more importantly, as the size will go down, we didn't decrease it significantly here, but as the size will go down, the radiative loss will be prohibitive. Now, moment you put metal around it, the mode gets squeezed, so the mode gain overlap is better, but the loss in the metal reduces the Q to about 180 from 875. Of course, there is another mode, which is a plasmonic mode, which we'll touch upon later in the presentation. So our idea is to introduce a low index dielectric shield between the gain media, this is the red box, and the metal, the grayish. So what happens when I introduce this low index dielectric? I basically reduce the amplitude of the evanescent tail on the metal. So I reduce the metal loss. At the same time, I slightly reduce the mode overlap with the gain media. But as long as the loss in the gain is less than the gain in less loss in the metal, I'm winning. So there is an optimum at certain thickness of the shield layer, I'm gaining. So the second, so we basically optimize the size to get the shield at the optimal value. The second thing that we exploit here is the creation of a photonic mode. We need to have some kind of a resonator. So we don't want the radiation to propagate away from the gain media. So to achieve that, we basically use a simple idea of a waveguide in cutoff. So this is classical impedance mismatch, and all the field is reflected. So all energy is stored in the gain media region. So these are the 2 basic ideas. I'll walk through with you what we have done. We basically analyze analytically a composite waveguide that consists of gain core, dielectric shield, and metal coating on the outside. Of course, the gain has positive dielectric constant, imaginary part, and metal has negative to indicate absorption. The modal structure can be solved analytically, and from the propagation constant extracted from the analytic solution, we find that the threshold gain is when the losses in metal are compensated by the gain. And this is a simple relation that the imaginary part of the gain has to be equal to imaginary part of the losses, normalized by the mode overlap with metal and gain media. So that's one thing, and I'm not going to walk through, I said it. So this leads us to some optimal value of the shield, as I was mentioning earlier. And when we look at different modes this waveguides, composite waveguide supports, we can see that the best mode that requires minimal threshold gain is the red line corresponding to HE11 mode, but unfortunately that's not the whole story. We need a resonator. So once we bring the resonator into the game, and as I mentioned, resonator is when this metal waveguide with low index dielectric is in cutoff. It's a closed version. This is open version, makes no major difference. When we bring the resonator into the picture gets changed. So here is the plot of the cutoff radius as a function of a radius of the waveguide. So basically, we change the radius and calculate the real and the imaginary part of the propagation constant. In this case, in cutoff, we want the real part to be 0, no propagation. So this is achieved around here, the minimal distance. In this case, at given radius for each of the modes, we determine where the cutoff is. And if you look now where the best mode is, it's a TE01 mode. So that's what the mode of choice that we choose to make the laser. This is, again, a plot of other modes, and you can clearly see that the Q for the TE012 mode is the highest. So we now use COMSOL to do more rigorous design to include the material parameters and all the materials and sizes. Originally, we used gold. Gold is tough material to integrate with silicon dioxide. You need some adhesion layers, which is not desirable. So we switched to aluminum. It's about the same at 1550. So these are the results of fabrication, summary of the results. This is the gain media after etch. Zoom in on one of the lasers. And this is indium phosphide pillar. Then we cover it with silicon dioxide and sputter aluminum. Then glue it to a carrier substrate or microscope slides or something like that using SU8. And then chemically etch out the indium phosphide substrate. We end up with the hole where the pillar was. So after making the lasers, we characterize them. And this is, again, very typical laser performance. I'm not going to go through details. It's certainly lasing. And the S shape of log-log plot of light-light curve is a clear indication of lasing action. So, so far we did it optically pumped. If it's not electrically pumped, probably not very practical. So we redesigned the whole semiconductor wafer to be able to enable us to do electrical pumping, current injection. So it was P and N indium phosphide contacts to the indium gallium arsenide gain media. To get the cutoff, now it's tricky because it's high index dielectric. To get reduced effective index, we need to undercut the indium phosphide such that there is no propagation of the mode into this direction. So that's what happens. And if we don't cover with metal, This is the plot of the simulation showing that the mode is really sitting quite a bit in the air, in the low index dielectric in this case. The mode overlap with gain is 38%, and the Q factor due to radiative losses is about 20. Once you put metal, interesting things happen. The overlap improves, but the Q factor goes up significantly. So factor of 22 reduction in threshold gain is appreciable. So I'll skip that. We built a bunch of lasers and packaged them, wire bonded them, put them on this packaged device, and put it into a cryostat. It did not blaze at room temperature, so we wanted to see what happens. Of course, larger size lays at room temperature, but not this particular size. So it lays till about 140 degrees K. We are still working on it. We are pretty much confident that we'll get to lasing at room temperature. I'd like to share with you a couple of minutes the threshold at coaxial nanolaser that is, again, optically pumped, but it's a very interesting approach to making nanolasers. So this basically is utilizing a coaxial waveguide as opposed to regular cylindrical waveguide geometry. Now, what's unique about coaxial? We use it in TV at home. What is the wavelengths of RF signal that it transmits? Probably meters. And the cable diameter is about a quarter of an inch or half an inch. So there is one mode that coaxial waveguide supports, is TEM-like mode. So utilize, if we want to build a laser that supports only one mode, that when I have a emitter in the resonator, I want it to be emitted into one single mode, no mode competition, no all other things, which I will reflect at the end. Why? That's a resonator of choice. So that's the resonator that we investigated, and we actually made two designs. One is structure A that supports the TEM-like mode and degenerate HE11 mode. So just to compare the two designs. They're not much different in scale, but the sizes are adjusted such that the degenerate mode is pushed away from the spectral window of the gain. So now we have in structure B only one choice. Anything emitted goes into this TEM-like mode. So here are a couple of reasons why you want to do it. If you look at the beta defined by spontaneous emission into the lasing mode over the emission into this same lasing mode plus other cavity modes plus emission into the free space continuum of modes. Now, in our lasers, the interface between the resonator and the free space continuum is deeply, deeply subwavelength. So this term can be asymptotically assumed zero. By getting rid of this other cavity modes, you end up with beta equal 1. And that's very exciting and interesting. So here are some results. At room temperature, the larger structure A, this is the spectral evolution, this is the typical lasing, and the blue curve is the prediction from the rate equation. So you clearly see the PL, the ASC, and the lasing. When you reduce temperature, the king gets shorter, but still very similar behavior. However, when we turn on the smaller structure that supports only one mode, although at 4 degrees K. When we start observing the emission, it is same line width as we increase the pump of the nanolaser. So this brings a hypothesis that it's a thresholdless operation of the nanolaser. The true proof of it will be done soon. We are in process of making some new experiments to to validate this hypothesis. I'd like to share with you in the remaining few minutes how we looked at the Purcell effect. And this is the approach we've taken. Of course, let me say a few words about the why Purcell effect. I mean, there is a well-known paradigm that when you get very small resonators with very high Q, your radiative lifetime goes down. So, and that's a good thing, because then there is no time for a combination, your efficiency will go up and whatnot. Okay, so that's a good thing. So we decided that we want to better understand it, went and did our own analysis using the emitter field reservoir model. It's basically a two-level system in a resonator, and the corresponding Purcell factor we calculated. And this is all true, I want to tell you, at transparency. Not before its transparency and not above transparency. The gain is just at transparency. It's not trivial problem to do it rigorously. And the other two regimes where we are still working on it. So that's the result you are getting. And the result is, as usually, inversely proportional to the volume of the mode, but it also is proportional to the double convolution of homogeneous broadening, inhomogeneous broadening, and the line widths of the cavity. So in the literature, however, they are using this equation in most of the cases, us included, before we found that it's not quite valid in semiconductor lasers. This is a good relation for solid-state lasers, where the absorption can be sort of assumed to be minimal. In semiconductor lasers, the absorption is dominant before transparency. And that transparency even, that's the equation you are getting. So it's not probably appropriate always to use this expression. So we did this analysis and calculated our own estimates using this formula in this Nature Photonics paper, which we estimated in the supplementary material to be around 8. When we did a more rigorous calculation, we ended up around 0.2. So that's not very impressive. However, revisiting again this equation we discussed earlier, we looked at our designs more closely in the light of the new approach to describe the Purcell factor, and we found that by careful design, you can increase the beta to around 0.3, I can't read it, 0.359. So that's good news, and we are still working on some more optimized designs that we can get beta close to 1. So that's basically brings me to one of the last slides on challenges. Well, there are plenty of challenges. The electrically pumped, the co-optimization, because so far we did a lot of thermal analysis. The lasers, luckily, because there is metal, they don't heat up. That's a big advantage of these lasers compared to VCSELs. Now, on the other hand, the properties of materials are changing with temperature. So this has to be fed back in the design and optimization. So we are working on that. Well, there are ways to increase model overlap other ways and make smaller structures. And of course, there are lots of fundamentals, but that we still are learning about. Like we are building a system to perform G2 measurements to determine the statistics of the source. And of course, the effect of emitter environment on spontaneous emission beyond the transparency is another interesting problem. So before I conclude, I'd like to acknowledge my colleagues, students who actually did all this work. funding agencies and our Nano 3 facility at the Qualcomm Institute at UCSD. And I leave my conclusions for you to read. Thank you very much for your attention.